Hello, everyone. Thank you for coming to our session. So I'm Micah Cornfield, and my colleague Anoop Johnson, I think, is to my left, if I'm looking at the screen properly. Today we're going to talk about Google BigQuery and our journey with Apache Iceberg. So just as an overall agenda, to get a sense of what we're going to talk about, we're going to give an overview of BigQuery for those unfamiliar with it. Then we're going to talk about BigQuery's implementation of Iceberg from a read perspective, and then customer challenges with Iceberg and how we went about solving them, or some kind of broader emphasis as things we can discuss with the community to continue pushing forward. So hopping right in for BigQuery overview. So BigQuery is Google Cloud's data warehouse product. It serves as a whole host of features. Kind of at its core is a managed storage engine and a query engine, which is the Dremel engine, which is one of an older paper that Google released a while ago that inspired a lot of open source software like the Parquet file format and Apache Drill and other things. And then on top of those, we have all the data warehousing features that you would expect, fine-grained governance controls with column level and row level security, and then additional features like ML and just generally high scalability. At more of an architectural level, things that the core of BigQuery that make it a robust and fast solution are kind of Google's Google infrastructure. So it runs on top of a petabit network, and we have clusters, large clusters of compute and large clusters of storage, which are disaggregated. We also, and then kind of for the ingress, we allow for bulk loads from object stores and for streaming. And we allow for writing back out to object stores and also entire managed storage component. People interact with it through a variety of APIs. We have our own custom UI, CLI. There's also ODBC and JDBC drivers, and we support client libraries in a bunch of different languages. So from more of a architectural, what happens when a query gets run in BigQuery, it starts off at job server, which receives an incoming query request. The job server coordinates between our internal catalog and Dremel engine to actually run the query. Queries get executed in stages where they read from either a distributed file system or an object store. Then they, as it gets read, and depending on the complexity of the query, it will go through several shuffle stages for things like joins and aggregations, and gets read back by workers. And then at the very end, we write it back to either our internal distributed file system CNS or to object stores, depending on what the user requested. So for now, talk a little bit about BigQuery's Iceberg implementation and how we went about doing it. So BigQuery already has a lot of different input sources. So there's already an abstraction called table defs internally for Dremel that allow us to wrap work. And so a lot of the work for implementing Iceberg is implementing a new table def. And at a high level, we there's an expansion API which takes some underlying data source and divides it up into units of work. There's an execute API which takes those units of work and gives back data for them. And then there's a get schema to understand what the actual schema of the data is. And it's important to note that when you call expand, this is a control plane operation that executes a data plane operation. So the execute is actually distributed across the cluster so that we can parallelize effectively and execute the queries within users' expectations, even at petabyte scales. One of the one of the first challenges with Iceberg was that the source of truth for the schema, not just that kind of the data table level, but in our catalog is external. Prior to this, all of our federation assumed a fixed schema within BigQuery. So we had to make changes across the stack that I just showed you to kind of assume that we couldn't rely on what we had already cached, but go back to the Iceberg as the source of truth for the table. Now, again, to kind of even more implementation challenges. So when we started the project, there were no, and there still aren't any really native C++ libraries for reading Iceberg. This is changing. It seems like the Rust implementation is coming along strongly, and we might, and so that's an exciting development, I think, especially now with a lot of query acceleration happening in native, both with things we see in Spark with Comet and with Velox and including having first-class native support for Iceberg will really drive adoption further. So because there's no C++ library, we had to rely on the specification, which was actually a very nice experience for us. We were able to do an MVP of reading Iceberg data simply by reading the spec. We didn't need to look at any of the reference implementations, and it just kind of worked out of the box, at least for like an initial implementation. Also, we're very happy with Iceberg spec in a lot of ways. We'll talk about a little bit this later, but like we're easily able to extend our integration with Iceberg to support materialized views on top of Icebergs. There's still some gaps, and I think as the Iceberg community grows, it'll become more important to really emphasize the specification first. I think at least the reference implementation in Java Iceberg supports GSIP JSON files. It's still not really mentioned last I checked in the Iceberg specification. There's still some ambiguity around partitioning data, where whether you're required to use identity partition data in scans and whether identity partitions are actually written out to the underlying data files. And then in general, one of the things that I've seen work well in other projects, my main experiences with Arrow is having a specification correctness test. So, which is also something that I think there's been some discussion on the mailing list, but I'm not sure it's come to fruition. And this becomes even more important as we're seeing other implementations in Arrow like Go and Python, and in Iceberg like Go and Python and Rust, to make sure that everything's reading and writing according to what one would expect. And so there aren't like one-off differences depending on what libraries people choose to bind to. Another interesting issue that we've kind of had a little bit of a journey on is how to expand the Iceberg data into units of work. So, first we need to parse the JSON metadata file, and then you get a manifest list, and then a list of and then that gets translated to manifests. And so at first we were doing that in a single threaded manner, and that works pretty well for reasonably, I guess, medium-sized data, you would call it. For some of our larger customers, we were seeing that as a significant bottleneck, and I think the Java library addresses this with multi-threading. Our model in Dremel is a little bit different, where we don't really do a lot of multi-threading. By its nature, we depend on distributed compute for our parallelization. So what we ended up doing for distributing the workload is we effectively run a separate query against Dremel to find all the units of work and then return that via the API. And then the last thing that we're considering that would be useful for some just exploratory data analysis use cases is just-in-time expansion. So the first two are a blocking step in queries. You have to complete the expansion before you can actually run any data, and that's for the purposes of gathering statistics and other things that help formulate a query plan. But in some cases, just getting units of work as soon as possible, we feel will be beneficial. Okay. The next challenge, and this I think comes up a bit, and I think this is something that the community is unifying around, but is working with catalogs. Because BigQuery is a multi-tenant service, it's a little bit hard to hook up to one-off instances of, let's say, Hive Metastore or even a REST catalog. We really, the options kind of devolve into having customers set up some sort of proxy, because most customers are hosting their metastores in some sort of virtual private network, or the preferred thing is having multi-tenant catalogs that we can connect to, so that it's a frictionless experience and customers can just provide credentials for that. So in order to address this from BigQuery specific offering and on GCP, we started building our own multi-tenant catalog, Big Lake Metastore, and we're expanding that to kind of next generation BigQuery Metastore. So we'll have a unified view of all of BigQuery's traditional tables, along with open source tables, both for supporting Iceberg and more traditional workloads like Hive and other potentially other open data table formats. And it provides all the nice scalability of BigQuery's Google's infrastructure, built on top of Spanner, which is our massively parallel SQL transactional engine to service a lot of those requests. Going to talk a little bit about what we did with materialized views as well here, just because there's been a lot of interest in the community a little bit. This might inform some opinions, but the way materialized views work on top of Iceberg data is at some particular snapshot, we do a materialization into our managed storage engine, and that is if the table's partitioned or the materialized view is partitioned, we store partial aggregations at partition levels. And then when somebody runs a query, so if somebody ran a query kind of at the send point, we see that there was an append to partition 1, delete to partition 2, and append to P1 again. We go ahead and at query time, we find the diff between what's in our pre-aggregated table and what we need to do. So in this case, we rewrite our scan planning to take the partial aggregates from P1, the two different appends, and aggregate those into the final results for the first partition. And then because P2 had to delete, we don't really have the ability with the sketches that we store of the data. We need to do a full rescan of P2, which is relatively efficient because we can prune out all the data files that aren't in that partition to do that scanning. So now talk briefly about some of the customer challenges that we saw more for their adoption in Iceberg and as a whole. So very wide schemas. Kind of the use case here is feature stores, but some customers also have wide schemas for other reasons. Talking about high tens of thousands of columns and growing at a very consistent basis. These can be hard to work with Iceberg without either a lot of tuning, and even there's just some fundamental issues that make the format hard to work with. So the JSON metadata files become really large to parse. There's some optimizations you can do there by doing streaming parsing to just get the bits that you need, but still relatively high overhead. The Avro metadata files, like manifest files, also become huge unless you're very careful about turning off statistics and other metadata that might not strictly be necessary, which again adds to bottlenecks. You can't do any sort of projection there. And then in addition to the metadata level reads, data level data level reads are also slow, just because things like Parquet there can be high overhead for projections when projecting out columns, because you have to parse the entire footer. So some solutions here are both working at the Parquet level to make it better for supporting wide files and some of the and also ORC potentially. And then thinking about alternate representations for the metadata at the Iceberg level to make them efficient. And I think it's come up on the mailing list. I don't think anybody's pursued it, but things like manifest files as Parquet files instead of Avro files, I think is still an interesting direction. Another big pain point we see is disaster recovery and replication. A lot of our customers are cross-cloud and they want to adopt a table format, but when they talk about kind of moving the data between clouds, they can't just copy it today and like update a pointer. They either need to go through, they need to effectively copy all the data files and then run some sort of update on the metadata to make that work, which is relatively complicated operationally. There has been some discussion here also within the community to support this, but I think this would benefit a lot. And even just for testing, it's very helpful to just kind of have golden test data and be able to copy it without having to do any sort of rewrites. And then the other kind of pain, the other thing that customers, when looking at Iceberg, kind of experienced are real-time streaming use cases. So when you have something like a Kafka queue, you want to see data kind of be able to query it immediately after it gets streamed in. And just by the nature of how Iceberg does commits, you have to kind of do more of a micro-batching approach, which has some pitfalls. And then just the grooming table optimizations. Some of our customers, don't find it a little bit painful to manage that type of thing themselves. So for the latter two use cases, Anoop is going to take over and talk about how we try to solve it on the customer's behalf.
Thank you, Micah. So that is some context. BigLake is an initiative from Google Cloud to unify data lakes and warehouses. Our overall goal is to make it really easy for our customers to maintain and operate a data lake at scale. So we BigQuery had a managed storage for quite a long time. We had several exabytes of data stored in it, and we have about a decade of operational experience. So through BigLake Managed Tables, we are bringing BigQuery storage to open data. So the user experience is very similar to how a customer would use a BigQuery native table, except that the customers can specify where the data should be stored. We support GCS currently, and we have plans to support S3 and Azure through BigQuery Omni. So, and the file format is Parquet, and connection is an entity that lets BigQuery read and write data in the customer buckets. So the tables, BigLake managed tables are read and writable from BigQuery as well as from open source engines. So the DML from BigQuery is kind of works unmodified on both BigLake managed tables as well as BigQuery native tables. For ingestion from external query engines such as Spark, we support a high throughput write API. And BigLake managed tables is Iceberg compatible. We provide Iceberg snapshots for external query engines who want to access this data directly from cloud storage. Next slide, please. So some of the key features of BigLake managed tables, as you would expect from a modern table format, we support schema evolution, time travel, etc. We also support clustering, where the records are ordered by the values of the clustering keys. This allows us to skip files more efficiently. Also, kind of speeds up aggregate calculations because it requires less shuffle. The more important takeaway is BigLake Managed Tables is a fully managed service. So there is no need to manually run, optimize, or vacuum commands. All of this kind of works similar to how BigQuery native tables work. The files are adaptively sized. For example, for very small tables, the file sizes are smaller so that the query engine has more parallelism to work with. For larger tables, the files tend to be bigger so that it compresses better. We support automatic reclustering. So as and when data mutations happen, and we run periodic background optimizations to recluster the data properly. We also do combining smaller files into larger files for more efficient reads. We do garbage collection. So any files that are deleted from the table past the time travel window are automatically claimed from cloud storage. Also, BigLake Managed Tables support the BigQuery storage read and write APIs. So the read API specifically allows you to read data in parallel from BigLake Managed Tables while enforcing all the row and column level security policies. So this enforcement of the security policies happens at the storage APIs, and the filtered data is sent back to the query engine. So there's no expectation of trust from engines like Spark. Write API allows Big Lake managed tables to ingest data at a very high throughput that's not typically possible with cloud storage. We'll get to that in a minute. As I mentioned earlier, Big Lake managed tables are Iceberg compatible. So we periodically generate Iceberg metadata and save it along with the data in the customer buckets. Another feature that's coming soon is integration with BigQuery Metastore. So BigQuery Metastore is a serverless unified catalog that's unified between open source query engines as well as BigQuery. So effectively, we are opening up BigQuery catalog for open source query engines. So for instance, a BigQuery dataset becomes a database in Spark, and a database can have tables that may be BigQuery native tables or Big Lake managed tables or open source Iceberg tables. Next slide. So let's take a view of what happens, how Big Lake managed tables actually work. So when a user issues effectively a DML in BigQuery, what happens is the query engine Dremel will materialize Parquet files in the customer buckets. And at the end of it, the engine has to commit the transaction. So the commit happens through a system called Big Metadata. So Big Metadata is the metadata store for both BigQuery native tables and Big Lake managed tables. So this is a stateful service. So effectively, the query engine makes an RPC call to Big Metadata to commit the transaction. The service makes sure that the transaction can be committed. It does conflict detection with other transactions and commits the transaction. So the transaction log itself is highly durable. It's replicated to multiple data centers for a high availability, and that's persisted. And this log itself is periodically checkpointed into a columnar baseline. So this is primarily for efficiency. This is kind of alluding to the metadata efficiency problem that Micah mentioned earlier. So when a user does a read query, effectively the query engine goes and finds out the last columnar baseline and then gets the tail of the transaction log from the service and applies these changes. So that's effectively how Big Lake managed tables kind of work. And so the source of truth is Big Metadata. And we periodically asynchronously generate Iceberg snapshots. We don't do it for every commit because that can be kind of expensive to do this inline in a commit. So this conversion from the transaction log into Iceberg happens asynchronously. And so basically, external query engines can access these data either directly from cloud storage through Iceberg libraries or can go through the read and write APIs. Next slide, please. So one of the common problems that customers run into is effectively dealing with streaming ingestion. So a common problem is cloud storage systems, almost all storage systems out there don't support efficient appends. So this leads to a trade-off that many of our customers have to make. The trade-off is typically between data consistency and efficiency. So if you commit too frequently, you end up having too many small files that you need to kind of go and combine later. It leads to a lot of metadata bloat. But if you microbatch too late, you kind of end up having stale data. So we have a purpose-built system in Google to kind of solve this problem. So this is known as Vortex. It's actually a distributed, replicated storage system for streaming rights. So the idea is to have a file system that's purpose-built for appends. So the system takes in records in a row-oriented format and uses this file system that has fast appends. And this data is actually replicated to multiple data centers for high availability. And the data that is returned into this write-optimized storage is visible immediately after a commit. So you could read the data with strong consistency. The way we extended Vortex to support Big Lake managed tables was to effectively periodically write this write optimized storage into Parquet. So effectively, a big lake managed table, the records are the union of tuples from the write optimized storage as well as from Parquet. So how frequently this conversion happens from write optimized storage to Parquet is a function of the ingestion rate. So for example, if it's a table that's highly active, the conversion happens very quickly. If it's a table that has a smaller write throughput, the conversion may happen a little slower so that we have a larger Parquet file. So we support ingestion only, inserts only currently. We also have plans to support upsert delete API. So where you can have an unenforced primary key and you can stream in upserts through the same API. So this feature actually is GA for BigQuery native tables. We are planning to extend this to Big Lake managed tables as well. Next slide, please. So another interesting part about Big Lake managed tables is how the Iceberg exports work. So as I mentioned, those exports happen periodically, and the metadata that's returned, the pointer to the Iceberg snapshots is actually registered in the BigQuery metastore. So if you are using Spark or Trino, there are two ways to read a Big Lake managed table. One is using it directly, using the Iceberg manifest and read the data directly from cloud storage. So this means it's an eventually consistent system in the sense that the Iceberg exports are typically stale and it's read-only. The other option is to read the data directly from the storage APIs. So that gives you strong consistency and also fine-grained row and column level security. But if you don't have a need for strong consistency or you don't need row and column level security, it's totally fine to go through the Iceberg read path. Next slide. So our Iceberg stories right now read-only snapshots. We want to do better. The two things we want to do is full DML support from Spark using open source Iceberg libraries. The second part is improving the freshness of the Iceberg snapshots we export. So if I were to make a wish list from the Iceberg, REST API might be to have two different APIs there, where you have a file level commit API that supports multi-segment transactions. So the client should be able to start a transaction and add, subtract files from multiple tables, and finally do a commit or rollback. So effectively, our internal metadata systems kind of work similar to this. That shows you how few ways are there to do certain problems. The second part is on the read path. We may want to have a query planning API that takes in a bunch of filters, applies the pruning, and returns statistics and the pruned files or unpruned files rather. So we are aware of a couple of proposals in the Iceberg community along these lines, and we are following them. Next slide. So to learn more about how Big Lake managed tables and Big Lake in general works, and also how the streaming system that I mentioned earlier, Vortex, we have a couple of papers in the ACM SIGMOD conference this summer. I'll put a link to the papers later. Big Lake managed tables is currently in private preview for allow-listed GCP customers. We are hoping to do a public preview soon where it's open for all customers. But meanwhile, please email us at this address if you would like to be allow-listed for Big Lake managed tables. Back to Micah. You're on mute.
Still have not mastered the art of video conferencing, even post-pandemic. I think a lot of the things we talked about, as Noop touched on, like the community is thinking about and addressing. I think one of the things that I see a little bit in the community, which is great, is like a large amount of consensus building. It would be nice to figure out if there's a way to, concretely move things forward without going back and forth and what those things are. Again, specification first is one of the reasons why we chose Iceberg as our preferred table format. We think there's a lot of value in having a specification, and that lots of different implementers can make work. And then there's still, like we just as a summary in the talk, there's still a lot of areas that can potentially be improved upon, and these are also things that are actively being talked in the community for the most part. Like wide schemas, I think, is a little bit less talked about. Started some conversations on Parquet, at least for supporting those, and then disaster recovery failover, as Nuke touched on, like abstract transactions, so that it's easier to separate out some of the direct things, some of direct accesses through Hive sort of things. So like having actual first-class REST APIs for that would be great. Streaming, I think, has come up a little bit, but I'm not sure it's like solvable within Iceberg by itself, as long as the commit mechanism or what it is, or it probably requires a fair bit of coupling to specific technologies. So that might just be an open question. And then recently, like the variant and JSON support, I think, and doing that efficiently is will unlock a lot of use cases for users. And with that, I think we are ready for questions.
All right, thank you guys. Very interesting. Just 2 comments about the slide. For streaming, you're right. But I mean, if you take a look on the Kafka, the tabular Kafka injector, it's using a commit coordinator that actually improve, I would say, the conflict of commits that we can have in streaming. But you're right. I think that first, it's very specific to Kafka because it uses another topic to deal with concurrent commits. So maybe we should have something at, why not catalog level, like something that can be shared by different ingester. So I agree, but yeah, the community is really talking about that now. I don't say we have a solution, but it's a fair concern. And by the way, we have a keynote session, a panel discussion later today, where we're going to talk about streaming, Jay speaking. So thanks for the transition. About JSON, just to let you know that in Spec v3, we are discussing about including JSON data type.
Yeah, I'm aware of that, and I think there's also like a variant and like some optimizations there. Like I said, I think the community is doing a great job from my perspective tackling these things. I think it's more of a like seeing these things land in the specification.
Yeah.
So and
but
for example, MVs, like rightfully so, like we want to get them right, but like the MV conversations have gone on for a long time, and they're still ongoing to kind of consensus. So.
Yeah, I agree. I mean, it's not so. I mean, it's not so easy because just storing the data type is one thing, but being able, for instance, why not imagining to have a transform that use a JSON element to do a partition? I mean, that's a fair use case. So I don't know if it's a good idea or not, but that's the question may happen when we discuss.
Yeah. Okay.
Questions on the chat. So the first, try to manage. We have few first table via Spark. Can any version of Spark, or does it have to? We have question.
I can. No, it doesn't have to be Google Meeting.
Okay.
So basically, the way it works, we have an open source Spark BigQuery connector. So this connector talks to the BigQuery storage read and write APIs to read and write data. And this is open source, so you could take this and run it on self-hosted Spark because it's an open source Apache V2 project.
Okay, cool. Thanks. Second question: are you adding any indexing for upsert or update support?
We are, upsert, delete is on the roadmap. Yes, I think the plan is to have an indexing support. Otherwise, the queries that need to coalesce data becomes much more expensive. So we are working on an indexing system that's internally BigQuery.
Yeah, okay, thanks. Last question we have on the chat is for existing Parquet tables in S3, is there any cost-efficient way to bring into BigQuery or BLMT?
Yeah, so we are working on a feature that's actually ready almost. In fact, it's ready, where you can ingest existing data that's in Parquet, could be high partition Parquet also, and you could add them to BLMT without doing an expensive read and deserialize back to Parquet. We call it rewrite-free loads or copy-free loads. So effectively, think of it as
All right, so that's thanks for that. Sorry, I'm flagging as answer. Okay, thank you. We have a new one. Access management question. Limitation to active. Not sure I understand.
So maybe I'll take this one and see if I can answer it. I think so my understanding, I think there's a proposal that I haven't been tracking lately to like build more sort of authorization mechanisms into Iceberg itself via the REST catalog. I think via tokens. It's something that I think Jack proposed, but otherwise Iceberg, as far as I know, it doesn't really have its own sort of access management associated with it. It's very coarse-grained in terms of like being able to vend S3 tokens or something like that. The access management that BigQuery provides is a lot more fine-grained, where it's not logically who can access files or things like that. It's a lot more about logically who can see what columns in the table and what rows a particular user can see in the table.
All right, thanks. I think, yeah, that's all for the question. So thanks again. Thank you guys again. Very interesting.